Video 1 in thermodynamics. The topic is computer calculation of ideal gas enthalpy and ideal gas entropy from a CP correlation with 4 parameters. And these parameters are for each pure component and we have a reference to the textbook at page 127, 203, and 212. This is the headline. The CP correlation we use looks like this. CP is R times A plus BT plus CT squared plus D times T in minus 1. That is equation 4 from the textbook. The reference state is 0 degrees centigrade and 1 atmosphere. And what is meant by a reference state? It means that if we take the enthalpy at the conditions at the reference state, that is 0 degrees and 1 atmosphere. What is the ideal gas enthalpy for 0 degrees and 1 atmosphere? That is what is meant by reference state, and that is 0. And the same for ideal gas entropy. If we take it for 0 degrees and 1 atmosphere, then the ideal gas entropy is 0 as a starting point. And then we assume that CP is constant in a 10 degrees temperature interval. From the correlation we see that CP is temperature dependent, but we assume that if we change the temperature by 10 degrees, then we can say that CP is approximately constant. And then we have a task, and that is to calculate the ideal gas enthalpy at 60 centigrade and the ideal gas entropy at 60 centigrade for example for pure nitrogen with known parameters A, B, C, D, and to find A, B, C, D that can be found in appendix C. So these 4 parameters, they can be found in for instance, appendix C. Then I start with some equations. We have a change in entropy from T1 to T2. This is an equation from the textbook stating that the change in entropy is the integral of Cp between the 2 temperature times dT, which means that the ideal gas entropy is the integral from the reference temperature to T of Cp, in this case ideal gas, dt. We assume that the Cp ideal gas is valid for that equation. Then we have a similar equation for delta S ideal gas. The change in entropy is the integral between the temperatures of ideal gas Cp over T dt. This is equation 514, and it's valid for constant pressure. And when we think of an ideal gas, we think about a pressure up to about 1 atmosphere. And then we get an equation for entropy from a reference temperature to T of Cp ideal gas divided by T dt. Now we have equations so that we can calculate the ideal gas entropy and ideal gas entropy. However, we haven't stated accurately how we do this, so I will then come with a suggested calculation procedure. Suggested calculation sequence. And in, for instance, Excel. If we think of using Excel as our calculation tool, I do not know if there is any integration routine in Excel, so we have to do this calculation and avoid the integration in detail. So what I then suggest is that we calculate the ideal gas heat capacity for each temperature interval. We can calculate this for 5 degrees, 15, 25, 35, 45, 55. Then to use this equation, we should use Kelvin. Then we take the integral equation from 0 degrees to 60 degrees. It is this equation. That is the definition. But we have to approximate, and instead we take the integral as a sum from I equal to 5 to I equal to 55 of Cp ideal gas times delta T in the interval, or that is the sum of Cp I ideal gas in the 6 intervals times 10 Kelvin. So that is calculation of the ideal gas enthalpy. And similarly, we calculate the ideal gas entropy as the integral from 0 to 60 degrees of Cp ideal over T dt, which is approximately equal to the sum from 5 to 555 of Cp Ig over T times 10 Kelvin. So that is the suggested calculation sequence if we should use Excel. However, this is only an approximate solution. So if we had another tool with an integration routine, I will have another suggested calculation sequence. For instance, if we could use a program like MATLAB, with a calculation tool, with an efficient integration of a function routine. This sequence is based on that we do not have any numerical integration tool. Then if we have a integration tool, then we can calculate the ideal gas enthalpy from 0 to 60 degrees of Cp Ig of equation 4.4. Equation 4.4 is this equation. In textbook, page 131, we have ICPH as a function of T0, T, A, B, C, D times R. This is a routine that makes it possible to calculate the ideal gas enthalpy. And then, similarly, we can calculate the ideal gas entropy by a function calculating equation 4.4, and we divide with the temperature dt. So, using Excel, we can get a solution or a calculation like this. If you use MATLAB, we can end up in calculating an expression like this or this for ideal gas enthalpy and entropy. So, this is the end of thermodynamic video 1.